All right, today we're going to consider the last part of our probability unit. We're going to address 3 different standards today. The first one says to understand that 2 events A and B are independent if the probability of A and the probability of B occurring together is the product of their probabilities. So remember, and is intersect, and product means to multiply. The second standard says to understand the conditional probability of A given B as the probability of A and B, now remember that's intersect, divided by the probability of B, and interpret independence of A and B as saying that the conditional probability of A given B is the same as the probability of A, and the conditional probability of B given A is the same as the probability of B. And what that's saying is that even if we're given A or B, the other event will have the same probability when we're given it. And the last standard is talking about constructing and interpreting two-way frequency tables of data, which we'll be working with today. So our essential question is, how do you determine if 2 events are independent events? And that's our goal for today, is to be able to tell by looking at different events if they're independent or not. Before we can do that, we need to know what independent events are. So the first part says 2 events are independent events if the occurrence of one event does not affect the occurrence of the other event. For example, if we roll a number cube and get a 1, it will not affect being able to choose an ace from a deck of cards, so those would be considered independent events. And we want to use the second standard first. Go over that since we've been working with conditional probability. So we know if 2 events, A and B, are independent events, then the fact that B has occurred does not affect the probability of event A, because that's what independent events are. In other words, if A and B are independent events, then the probability of A will be equal to the probability of A given B. And we can use that to determine whether 2 events are independent. So let's look at some examples. Here's our first example. An airport employee collects data on 180 random flights that arrive at an airport. The data is shown in the two-way table. We want to know, is a late arrival independent of a flight being an international flight? So we're going to be looking at a late flight and an international flight. So look at the table. What do you think? Do you think being late is going to make it be an international flight or have some sort of effect on that? So let's look at it. Look at this situation where it's spelled out for us. Let's let event A be the event that the flight arrives late. So let's put an A on the table. That always helps me to label my table. And let's let event B be the event that the flight is an international flight. So, in order to do that, here's our steps. To find the probability of A, first we need to find out the total of flights. In the table, the grand total right here is always in the corner. So there's a total of 180 flights. Next, of these flights, there is a total of how many late flights? Well, late flights is our event A, so if we go to the total column, that would be 18 late flights. So the probability of A late flight, would be 18 late flights out of a total of 180 flights. So 18 over 180, which reduces to be 1 over 10. Now let's consider the conditional probability. To find the probability of A given B, first note that there is a total of how many international flights? Well, that's event B. So if I read the chart over to event B, I know there is a total of 60 international flights. And of these flights, there's a total of how many late flights? So in the international row, there are 6 late flights. So the probability of a late flight, given that it's international, would be 6 late flights out of a total of 60 in the international row. And that reduces to be 1 over 10. Now the standard tells us that if the probability of A, which is late flights, is the same as the probability of A given B, which is late flight given it's international, if they're the same, they're independent. So being international does not affect whether the flight is late or not. Here we want to look at the second standard, and to me it's a little bit easier to use. You're looking at a tree diagram to help understand the formula for the probability of independent events. For example, consider tossing a coin 2 times. The outcome of one toss does not affect the outcome of the other toss, so we know that the events are independent. The tree diagram shows the probability of a coin landing on heads on both tosses is 1/4, because here are my total outcomes. I have 4 outcomes, and the only time that I will get 2 heads is 1 out of 4. So I know the probability of tossing a head and a head, or the intersection of heads, would be 1/4. And the key to our understanding, being able to use that second standard, if we know the probability of A and B, or the intersection of A and B, is 1/4, we can know, it tells us that we can use the product of each event. So the probability of tossing a coin and getting a head is 1/2. That's event A. And tossing the second coin and getting a head is also 1/2. And we know that 1/2 times 1/2 equals 1/4. Therefore, the intersection's 1/4, the product's 1/4, so these are independent events. Now, to me, using the product of each event equal to the intersection is easier, so we're going to focus on this one. If you spin a spinner at the right 2 times, what is the probability that you spin an even number on the first spin, followed by an odd number on the second spin? So remember, this is an intersection. So event A would be an even number, and event A would be an odd number. The first thing it wants me to do is find the probability of event A. So if I look at my spinner over here, I see 1, 2, 3 even numbers. So that would be 3 out of a total of 8. And event B would be the odd numbers. So I have 1, 2, 3, 4, 5 odd numbers. So that probability would be 5 out of 8. So if I want to find the probability of the intersection, getting an even number and an odd number on the second spin, all I would have to do is multiply the 2 probabilities together. So we found event A, an even number, was 3 out of 8. And event B was 5 out of 8. And if you need to use your calculator, you can simply multiply the numerators. 3 times 5 is 15. And 8 times 8 is 64. So the probability that I spin the spinner and get an even number and an odd number would be 15 out of 64. We know the outcome of the first spin does not affect the outcome of the second spin. Therefore, these are independent, and I can use this formula. Okay, we want to prove that the two-way table shows the data from the first example. Show that a flight arriving on time and a flight being domestic are independent events. All right, so if we label the table, on time would be A, domestic would be B. Let's define them. On time would be A, domestic would be B. Now we want to prove that. We can use the chart to find the intersection, the probability of A and B, by finding the intersection of on-time domestic flights would be 108 out of a total of 180. So I would write 108 over 180. And we want to prove that that equals the probability of A. Now, remember, to find your probabilities of each event, you have to go to the total. So if I take my own time, event A, that's going to give me 162 over 180. And I need to multiply that by event B, which is in the second row. So that's going to be 120 over 180. And what we need to do is get our calculator out and multiply them together. So I would multiply, hit my fraction bar, 162 over 180 over times, fraction bar, 120 over 180. And I would find that equals 3/5. So I know the product is 3/5. Let's see what happens when we reduce 108 over 180. And I find that also equals 3/5. So since the intersections equal to 3/5.